So once we start compilation, it do 4 main tasks. One is analysis and synthesis. So analysis, as we know, it check the code is as per the VHDL language or not. It analyze, and synthesis, it convert the Verilog tool itself convert into the gate level netlist. And second task is filter, place and route. So in that place and route, it check in a specified selected device where it fit the logic. And third is assembler. So assembler, as we know, it generates a programming file for that particular device. If a PGA chip, then programming file format is SRAM object file. And if it's a CPLD programming device, then for that programming file is .POF, programmable object file. As we know, FPGA, it is a lookup table based device in which lookup table is nothing but the SRAM. So in FPGA, it generate a .SRAM object file. And the CPLD is a non-volatile device that generate a programming file for it. It's have a programming that devices as a switch. Then lastly, the classic timing analysis. It generates the report for the delay, delay between the input and output pins. Right. From this delay, we can say for what maximum frequency we can operate. So once full compilation, once you do, it will show you the report. How many logic cell required to implement our device? How many IO pins required to implement our design. Once the compilation is complete, next task is to simulate or to check for functional checking. Right. So for that we have need to give one file through the input. So go to an input and select the verification and debugging types of file. Right. So here let me verify our design using the vector waveform file. So we select the vector waveform file. It will open a editor window where we can have different port. Right. So let me insert the port or node or bus, and by finding the node and bus, and let me find from the our module traffic underscore control. So it will list out the different ports, whichever we have list out in a traffic underscore control module, and select all the port and okay. Now okay. So we have a input is initially is logic 0 by default, and output is unknown by default. So here this n underscore e underscore light, n underscore light, s underscore light, 7 segment, and w underscore light are the output. So it's by default value is a default simulation, it is unknown. And for the reset and clock, there are the input port. So by default value is a logic 0. We can assign any value. So let me assign for reset. Initially, let me make the reset 1 for up to the 30 nanosecond, and let me assign the clock. Okay. After giving the input for which these are our nothing but our test or a stimulus, right? So after giving the input, save this vector waveform file. Okay, save in the same folder where we have our design file or project file. Then we can perform here timing simulation and the functional simulations. So difference between the timing simulation and function simulation is functional simulation, it only check the logic as per the logic without the delay, and in timing simulation it gives you the output with the actual delay, right? So let me check a functional simulation. So for the functional simulation, To do the setting of change in the mode of simulations, go to in a assignment and setting, and have a functional simulation bodies. And for the functional simulation, we need one file. It is a gate level netlist, right? Functional simulation netlist. So generate this file before the simulations. Okay. After the successful generation of function simulation netlist, simulate the design and check visually in a web form. It is we are getting output as per our design or not. So when having a reset, what we want in when it's in a reset, we want north underscore light green LED would be on, and the for the rest of direction, yeah. So here you can see for the north here 001. So it green LED of north is 1 and the yellow and red is off, and for the rest of direction light red LED is 1, and depending on the count it's have its 7 segment code, right? And after the 8 clock pulse, once we reset is deactivated. After that it start after the 8 clock pulse. So up to the 8 clock pulse here might be you can visible. So this 8 for the 8 clock pulse, this n underscore light output is 001, means it green LED is 1, and for the rest of direction red LED is 1, right? After the 8 clock pulse, it goes into the north underscore y. So, and it stay for the 4 clock cycle. We have designed such a way that it should stay in this state for the 4 clock cycle to give the holding, right? So here you can see the north LED is 1, output is middle bit is 1, and red and green LED is 0. And afterward it change the state and it goes into the east, right? So you can see after this here east direction LED will be the 1. So this is a output. We can verify this is a verification of the design visually. Now suppose if you want to implement on a chip, right? We have a FPGA board. So also we can implement it. So let show you the FPGA board. 1 minute. Okay. So to implement on a FPGA board, first task is to let me show you the board which we have. So board which we have, it is a D1 development board developed by Altera. Now Altera is Intel has take Altera. So now the company is Intel. This board in a laboratory which we have. Now we are going to implement our design in this board, and you can see in middle have the Cyclone 2 FPGA chip. It is designed using 90 nanometer technology, and have a different peripherals to give the input output as well as to different peripherals to interconnect with another board. And inside the board have a 3 crystal for the clock. So it's a 27 megahertz crystal. One is 27 megahertz crystal, another crystal is 50 megahertz crystal, and third one is the 24 megahertz crystal. Right. So if we have any clock is required, we can use this internal clock, internal crystal as a clock generator, and we can use that for our design. So in this our design itself, we required a one clock, but if we give this clock directly to our design, so it is a 50 megahertz clock, and we cannot able to see the change in a state. So we need at least some delay in terms of second to visualize, right? So we need to be divide the clock, the 50 megahertz clock into a 1 hertz clock. So need to be designed one small Verilog program that for to clock divider. So that also we'll see how to be designed and how you can use that. So this board we have. So let's see. Okay. So let me implement this in our board. For the implementation, we have to do a pin assignment, because if you see in FPGA, this FPGA have a more than 300 IO pins. Out of 300 IO pins, some IO pin is connected with this LED to see the output. Some IO pins are connected with the switches to give the input. So we need to be see which pins of FPGA is connected with the switch and which pins of FPGA is connected with the LED. Right. So let's do the pin planner. So here we have to assign. So suppose as a clock, let me use as a clock as a switch, right? So we have to see in its manual pin configuration given. So here SW0. So this is a first switch. Here you can see this first switch. So first switch, it is connected with the L22 pin number of FPGA, right? L22 pin number of FPGA. So let me use this first switch as a clock. So here L22 location. Let me use a reset. This is our another input, right? So let use this reset as a another pin, another switch as a reset. So here L21. So let me L20. Now rest of are the output to see the output, right? So let me see the output. Zeroth bit of each direction output, it is a green LED. So we have provision in our board have only the green and red LED. There is no any yellow LED. Otherwise, I can make it more visualize. Make you for more visualize. Have the green, red, and yellow LEDs. So I will use the green LED for the to display the green that for all the four direction, and for the rest of for the yellow and the red for all these four direction, I will use the red LED. So let give here have the yes here have the red LED. So let me use this two red LED, and let me give this two MSB bit. Right, so it is one MSB bit is red and second one is the yellow. Similarly, we use the next two LED for two north direction, red and yellow. Then we can use next two red for the south direction, red and yellow light, and for the west, let me use next two for the west. Now let me use the green LED to display the green light. So we have the green LED, green LED 0. Let me use for the first the north, and green LED 1. Let me use green LED 1 for the east direction traffic, and then green LED 2 will use for the south, and last green LED 3 will be used for the east direction traffic. Now here I have the 7 segment output. So we can use, we have in board, there are 4 7 segment display here, right? So let me use this one of the 7 segment display to display the count in a form of a decimal value. So for this 7 segment, this is 6. Let me copy and paste. So after the giving the pin configuration, again compile the design, recompile the design. So go to in a processing and do a full recompilation. There are 2 types of compilation, full compilation and analysis and synthesis only. So when we are in the debugging mode, or when you in a verification mode, then do only the analysis and synthesis and check the functionality of the design. Once we'll get the correct functionality, then after do the full compilation, because in a full compilation it will take time. In a full compilation, it do all the tasks like analysis and synthesis, then the fitter, then the assembler, and the last plus timing analysis. So for that it take the time. So whenever you want to implement on any board, then need to be do a full compilation. Otherwise, it's not required to do a full compilation. So once our design ready in terms of functionality, right? Then after do the full compilation. So once recompilation is successful, then next step is to implement on a board. For that, I will show you. So I show you the step. Next step is, after the pin planner doing the full compilation, next step is go to in a tools, the programmer. So once you click on the programmer, so whatever the current project file you have compiled, it's a programming file which is the .sort. As I told, the Cyclone 2, it is a FPGA chip. So its programming file is .sort, SRAM object file. So it will come and set the hardware USB blaster. We are going to program to the USB blaster and click start. It will start programming on an FPGA board. Right now, let me show you the board. For that, I need to be stop screen sharing. Then I can make it visible for the sharing. So here. Let's see. So this board we have one minute. Let me. Okay, so the programming cable is a USB blaster cable through which we can program it, and this is the board in which we already have downloaded our design, and these are the different switch we have a use for the reset and the counter, and these are the LED we have a use for the output to display, right? So at present you all can see one green LED is one, which is the north direction by initialize, and 3 red LED for the other directions traffic. Now this first switch I have used as an clock, and next switch I have used as a reset. So I reset it. If I give the clock, it will not change the state. If I give any clock, it will not going to change the state. Right? I will try my best to show you if it can. Okay. Yes. So here you can see if I reset is on, then giving the any clock by through the switch, it will not change the state. Right? Let make the reset is equal to 0, and then we'll give the clock, and we can see. Okay, let me give the clock, and we can. So you can see the change in that 7 segment display, right? After the 8, it will change the state of the LED. So here, let me give the another clock. So it change the state in output. Once it's reached to 8, then you can see it change the state. Now all are the red because we already have used the yellow as also as a red, right? That's why it is all in the red. Now it stay, then again go to in a next. So you can see the change in a state of LED. Okay? For the clock here. So by implementing on an FPGA, we can make it for the prototype, and we can check our any design. So this one is the today's first task, right? Implementation on an FPGA board and how to design. If you want to use, suppose you want to use a internal 50 megahertz clock, and if you want to down, it's using the clock divider, right? That also we can do by designing one clock divider. Okay, so let we have a one clock divider. Let me open. So this simple program for clock divider, and it is designed which divide the clock from 50 megahertz to the 1 hertz clock, right? So for that, if you see, we need a count value to convert 50 megahertz to the 1 hertz, right? We need a exact decimal 25 bits value. This is count value. So for that count value, it is stay for the 25 into 10 raised to 6 times. It stay in a logic 1, and for the 25 into 10 raised to 6, it stay in a logic 0. That many clock cycle. So total is 50 into 10 raised to 6, right? So it convert a 50 megahertz into the 1 hertz clock. So let me have a new barrel of let me say clock underscore divide. It is a file name. So let me save this file using with the name of clock underscore. Now let's create a symbol, and then let's close this project, and let me have a new project wizard for the clock divider. let me say here clock underscore clock 0. And let me create a symbol. And let me open it's in a block diagram file. Let me close this and let me open a new type is block diagram schematic file. Here we can insert there is only a clock divider in VLSI. Let me first create a symbol of traffic light controller. So here we have one clock divider and another we have a traffic light controller. Okay. Okay. So let me use the clock divider input. Two input is required. One is for the reset of clock and reset of. Also, let me use the reset of the traffic light controller. Output of this clock divider, that will be the input of clock as in a clock traffic light controller, and this reset, it is input, one of the input. Another input is reset of clock and the input of the clock. Let me give this name as an let's say clock. Let's give this name as a reset and reset for the traffic light controller and output. So here we can have the output. So we have to write the output. So we required a different 5 bus in output. Right. So here it is a bus. So let's first change the name. Size of bus is 3-bit, so it can be specified as name and in square bracket 2.0. So similarly here it is for the south, so 2.0. For the east, it is for west, and it is for 7 segment. And with this 7 segment is 6.0. Then connect this bus okay. After this, save this file In the same folder, you can give any name. Let me give as a graphic and create the project for this file and select the device in which we want to download. Right. So hierarchy types of design it support. We can enter the design using the block diagram entry. Next step is similar, same we have to compile the design. So let me compile our design. Okay, if you're having any error, it will show you in this block underscore output is undifferent. Okay, again save and compile. Once it's compiled, then after the procedure is same as we have did for the last project to implement on an FPGA board. Need 10 assignments. Right. So here, whatever we have assigned, we have to assign the pin assignment, clock, and reset, and everything, and then we have to implement on an FPGA. Okay. So let for the quick, we'll assign for let we have this X is already selected. Let me assign to this 4 bit of X, and for the LED, let us select continuous 3, 6, not making as a red and green and bifurcations to make it fast. Then and then 3 for the rest. Okay, and we require 3 switches, one clock. So for the clock we use an internal 50 megahertz clock. So right, because we'll give this as a clock divider. So after the clock divider, we'll get a one hertz clock. So the pin number of 50 gigahertz clock coming from the crystal and it connected with the L1 pin. So let me use this for the clock as an this internal clock. So not need to give manually through the switch. And to switch for the reset for the clock divider and for the traffic light controller. So once we'll assign the pin, then again need to be recompile the design. Once it's compiled, then download on an FPGA board. Okay. Next step is to go to in a tools programmer and download this file on an FPGA board. Let me switch on the camera to show you. Great. So you can see here not need to give the clock, it automatically change the state as well as it will be in a display on a 7-second display, because here we have used a internal 50 megahertz and we have divided into the 1 hertz. So at every second you can see increment in a 7-segment has a display as well as per our state transition, it stay in a green state for the 8 clock cycle, and for the yellow state stay for the 4th clock cycle, and according it change the state. That state change can be observed through the LED change in globe. So this is the step-by-step implementation on an FPGA board. So we have designed one design which is a traffic light controller and implemented on an FPGA. If you have any questions, most welcome. You can ask by unmuting your mic. So this is first part of this demonstration, and second part is I'm going to show you how to use the EDA playground. Okay, so hope no any questions. So let's see how to use the EDA playground. Right. Okay. So once you write in a Google EDA playground, right? Then it will ask you for login. I have already logged with my login. Let me log out first. So it will ask you for the login. If you are a new user, then go to in a register for full account. So once you click on a register of a full account, it allow to use if you have your organization ID. So all the professors we have their organization ID. So you have to use your organization ID for the full access of the EDA playground. So I have my organization ID is HP Koringa at the gcrajkot.ac.in. It will send you one test mail, verification mail on that ID, right? Then whatever the password you want to set and the detail about the institute and yours. This is very simple and small form that you have to fill up and click on the I agree. It will create a account and then go to in a login. After creation, whatever your mail ID, first of all, it will send you one mail on your mail ID, one link. You have to verify that your mail ID by doing some process which send on the link. By clicking on that link, it verified your mail ID. Then your login is ready to use. Then use your login. It will open this once you log. It will have one side on right hand side have a design file. Whatever the design file we want to design, and left hand side window for to write the test bench of that design, right? If we write only the design and if we run the simulation, it will run the design file and then it run the test file. So if you do not have written anything in a test file, so it run only the design file, then also it's okay, right? Also, so this is design file and it's a test file on the left hand side. It's our two window, design file and test file. Now you can see here we'll get we can have in a VHDL, we can have the design in a form of system Verilog and Verilog, in a specimen E plus SV and Verilog, Python and C++. So different language it support to enter the design. This is very good platform provided to learn, right? Most of even in industries, engineer are using this platform for to learning, right? Also, if you can see tools, so you can see there are various commercial tool available for the simulation purpose, which will not get easily in a freely. So here we can use any commercial tool to be simulate our design. Whatever design we want, that it can simulate through by using the commercial tools, right? Cadence, Mentor Graphics, and Synopsys commercial tools are available for to simulation purpose. as well as for the synthesis purpose also available. Free tools also available, right? So this is very good platform to simulate the design for to learning purpose, right? So you can explore in your for your student also that tool for the learn purpose. Hello, hello. So let us see how to enter the design, how to write it test bench, and how to simulate, right? So it also has some ready-made examples. So if you click on example, it's have an example on the for verification, for the design example, Python based, Verilog based, different ways examples are available. So let's take the example of Verilog and system Verilog. So here different example are available. Finite state machine based example, memory design example. Let's take simple example to understand how it works. EDA playground. So let's take a clock divider. Right. Sorry, D flip-flops. So D flip-flops, it's a design file. Right hand side window, whatever you can see, it is a design file of D flip-flop. So module, then the name of module and the port list. So this D flip-flop have clock reset and the data input and two output clock and clock bar, right? And then declare the port, input port and output port. Here we are going to use the it is a sequential, so always statement, always procedural, so need to be explicitly defined output as a reg. By default, input and output are the wire type. Then assign Q bar to this QB, which is a Q bar, right? Now in always, when we want to assign the D to Q, whenever have any positive edge of clock, right? Or whenever have the positive edge of reset, then we want to reset the output. So we'll write in always statement false edge of clock and false edge of reset. So if reset is activated, it reset the output by assigning Q with the 0 value. Else this right, else what we want to perform, we want to assign a D to Q whenever having a positive edge of clock, right? So it is a very simple Verilog code for the D flip-flop. Now it's a test bench. So in a test bench, as I explained in a morning session, so test bench, it's a module, and the test bench, the name of the module without the port list, right? And all the port of the design DUT have to be, all the input port need to be defined as a reg, and all the output port as a wire, right? Then the instantiate the design under test. So here we want to that put this our D flip-flop inside the test bench. So test bench is a top level module, right? So here we have to instantiate the design. Here using the mapping is a port name mapping, right? So the clock, it is an a port of the design file pin, and the clock this inside the bracket, it will connect with the clock of the top module, which is a test bench. Once we instantiate the DUT, next task is if need to be generate a clock, then for that we write one initial procedure to generate the clock. Okay. So here one initial begin, and then this dump directives, this dump file and dump variable, it is used to convert whatever we have here. We are displaying the data. If you want to display in a waveforms, right? So this two file is used to display on the waveforms, and this dollar display, it is similar like you see to display anything. So whatever you want to display, we have to write in a bracket two inverted comma. Then first let me assign clock equal to 0, reset is equal to 1, D is equal to unknown, and then display. So here the display is a one task, right? So it called the display. So once we write the task name, it called the task. So what? Let me see what is the return inside the task. So task is it is have one unit delay, and then it display the Q, display the Q bar, and display the D. So inside the task is return one to display the D, Q, and Q bar data, right? End task. So this is very small task is a return, and here we can call the task every times whenever you want to display the D, Q, and the Q bar, right? Then we release the reset, and by making the reset is equal to 0 and D is equal to 1, and then again we'll display, and then toggle the clock is equal to 1, and again will display. So this is a simple test bench of a D flip-flops with DUT and the stimulus block for to give the different test patterns. Now here I have also a provision. It can display the output in this window in a the text form, as well as we can have a open web to display the output on a web form window. It opened a one web form window once we run the simulation, right? So after that, click on the run simulation. It will compile the design, right? Design file, and then compile the test file, and as for the display and everything, it will be the display on this window, as well as we have returned the dump file, so it also open in terms of web forms. So here we can debug our design. It is giving the correct output as per the our design or not. So we can test, we can verify functional verification we can do. So you can see it. So it is a very good, I can say, platform to learn without need to install any tool, any EDA tool. As we know, in a VLSI, EDA tool is so costly, right? Simulators tool is still available, but other tools are costly. So here we can use some commercial tool to simulate the design. That is very good about this EDA playground. Right? So it is a very simple to be used EDA playground. Any questions in the EDA playground? It allowed to log in only for the your organization ID, not on a general ID. Gmail.com, that types of ID will not take or will not provide you a full support, right? Full access. So you can fill here whatever filling we'll have when we use any EDA tool, right? So that same types of filling will get in a any like a Quartus 2 or any tool, Mentor Graphics, Model Sim, any tool similar, the filling will get in this playground, EDA playground. Okay. Okay. So yes, any questions? Okay. So let me take one example. on a ADA playground, step by step how to in a ADA playground. Right. So different example also given here. You can go through it and you can learn many things using the ADA playground. Any questions? Any doubt? Okay, so let me so whatever I want to show you in this demonstration, I will show. Now let me complete our morning. Remaining presentation on the Verilog.
Excuse me, one question by Dr. Suresh Kumar. What simulator used? Which simulator is used?
In a EDA playground or in whatever we have, so it is a quarters 2. Whatever I have gone through a complete implementation in a board, that simulator was, it is the quarters 2 simulator from the Altera. Now it's Intel. And in a EDA playground, it's available different simulator. Right? Anyone we can, as I told, it's some commercial simulator is also available. So we can use in EDA playground free commercial simulator. But it's only for the practice purpose. Right? So to learn, it is very good to use the EDA playground. So friends, in a morning session, we have a time with us 30 minutes. So let me utilize the time. The session we have not able to complete in the morning due to the time limitation. Let me complete right now. Right. Okay. So I have a shared screen. Hope it is visible. Right. And let's start. So in the morning we have covered up to this, right? We have reached that relational operator. We have discussed about the relational operator. Right? So So can anyone tell me what is the difference between we have discussed this rest of you can see the operators relational operator you can easily understood because you have known different language. Here have the equality and case equality. This is different, something different, right? So what the difference between the equality and case equality is? In a equality, it consider only a 0 and 1 to check equivalence. If having a x or z, then it will give the output. Then it will be give the output. It is equal to x, right? And if you have the 0 and 1, and depending on that, if it's equal, then output is 1. If it's unequal, then output is equal to 0. And in a case of case equality, it include the x and z also to check the equality of the two number. But only in equality, it not included x and z to check the equality. So whenever the number having any number having x or z value, then it will give the output is unknown. Equality give the output is unknown. But in a case of case equality, it include the x and the z, right? So output is always only in a two form, either the 0 or 1. If the both the data is equal, then output is 1. If both data is different, then output is equal to 0. So that's the difference between the equality and the case inequality. Case equality. Hope this is clear. Next is logical operator. That is understood bitwise operator. That also understood. Now this is very much important. Verilog have some unary. There are three types of operator: unary operator, binary operator, and the ternary operator. So the operator which require two operand, it is called a binary operator. The operator which have only one operand, it is called a unary operator. So unary operator normally used for the reduction purpose, right? It convert a 8-bit, 16-bit data into a single bit. So suppose we want to AND all bit of A. Suppose we want to AND all the bit of A. Suppose A is a 8-bit data, and we want to AND all the 8-bit of A, and we want to assign the output to the Y, right? So if we'll get output is equal to 1, Y is equal to 1, we can say all the bit inside the data A, it is equal to 1. If we'll get output is equal to 0, then we can directly say one of the bit or more than one bit, it is 0 inside the data A. Similarly, yes, similarly have the OR operator, then XOR, XNOR, all this we can use. So XOR and XNOR we can use to check a parity. Suppose if you have a even numbers of 1, and if you are doing the XORing of that data, we will get the output is equal to 0. If you have the odd numbers of 1 in this out of 8-bit, and if we XORing all the that 8-bit, and then it produce output is equal to 1, right? So that can be used for to parity generator and the parity check from this 8-bit or the 16-bit of the data. So they have the unary operator. Another is the concatenation. We can combine the data and assign to the third variable, right? So suppose A is an 8-bit of data, and from this A, we want to use a 0th bit, right? And from the B 8-bit of data, and we want to use a 1 to 7th bit of B and 1 bit of A, and we want to assign to the C. So we can assign using these types of concatenation statement, right? So it will C will be the C will take the C is equal to, now first bit of C, because A is written as an left hand side, right? So A of 0 will take as an MSB bit here, it will fit here, and rest of the 7 bit will be the fit here, 0 to 7th bit, 0 to 6 bit of C. So it take this in order as per the return inside the curly bracket. Same way, if you want to read only suppose from this A we want to read 1 bit, and from the data of B we want to read that 2 MSB bit, let's say, and in a C we want to extra, C is also an add bit, but we want to fill the C with the remaining bit by the user defined, right? So we can write like that. If we write like this, A of 0, so it take this A of 0s as an MSB bit. Then suppose I want to feed, I have taken 2 bit here, 1 bit here. So total is 3 bits, so remaining is 5 bit. So if I want to feed 5 bit, user defined 5 bit, so I can feed it using writing in double inverted comma, and here it is a B 6, 7, right? So how it feed it 2 LSB bit of the C, it is 2 MSB bit of B, and the middle bit of the C are whatever the user specified, that will be here. So that also possible using the concatenation. Then have a support of shift operator. So it's have a left shift and the right shift, right? So A, this is the left shift of the data. So it is shifted left and add in append in a LSB, it add the 0. In a right shift, it is shifted the data toward the right and put a 0 append in a MSB bit, right? Then have the conditional statement. So in a conditional statement, it is a have 3 operands, right? So conditional statement, if you see, A is equal to, if this is a condition, C greater than D, it is a condition. So if the condition is true, then we will assign this first value to the A. Then this first value will be assigned to A. If the condition is false, then it will assign the second value to the A. Right? So suppose if you want to implement a 2 cross 1 mux, right? So in a 2 cross 1 mux, we know so selection line, it is our condition, right? Or a control bit. So if the selection condition is true, then it will assign the first value. If the condition is false, then we assign the second value, right? So we can write the assign out control. If the condition is true, means the condition is 1, control bit is value is 1, then we want to select the in 1 that we want to assign to the output, right? If the condition is 0, control bit is 0, then we want to assign the in 0 into the output. Also, we can implement a 4 cross 1 mux using this conditional statement. So here you can see the output. It first check the S1, right? S1 is the MSB bit of the selection line. So S1 is equal to 1. Then inside that conditional, it is another conditional statement. So it check the LSB bit of the selection line. If this is also 1, means the S1 is 1 and S0 is also 1. Then we want I3 that is assigned to the output. If the S1 is equal to 1, but the S0 is equal to 0, then we want the I2 is want to assign to the output. And the S1 is equal to 0, it will check this part. Right. In that again it check the S0 is 1, then it assign the I1, and S0 also 0, then it will assign the I0 to the output. So this way also we can implement a 4 cross 1 mux using the assign statement and conditional statement. In a Verilog also it's have a replication, right? Suppose we have a B, it is a one nibble of data, and we want A, which is the replication of B two times, right? So I can write a two that B and this. So it is replicate the B two times. So A will be the 1011, 1011. This is the value of A. Right. So hope it is clear what is the replications. Okay. So let's see how to implement a 4x1 mux using the data flow modeling. Right. So module input and output out here continuous assignment output must be types of wire, right? And if you not define output and input, by default it is wire. So if you define or not define, it will not give any error or the output will be the same. So in a data flow directly we can write the Boolean equations of a design. So this is the logic equation of 4x1. So directly we can write the logic equation. Also we can write in terms of the mathematicals. Suppose it's a full adder and A plus B plus C that assigned to sum and carry. So also we can write in terms of the mathematical. So here we can see we also it have included, right? So here it not specified output as a wire because output and input port, both the port by default, it is types of wire. So this is implementation of 1-bit full adder using the A plus B plus C, in 1 plus in 2 plus C in, right? So it will assign the MSB bit will assign in C count and LSB bit will assign to the sub. Last is the behavior level of abstraction, and it is widely used in a Verilog. Behavior modeling is widely used in a Verilog. Modeling the circuit, complex circuit behavior modeling is highly used. It is a higher level of abstraction modeling compared to the data flow and the gate level. And it's have two types of procedural. One is the initial and another is the always. So let's see initial procedure and always procedure. Initial is execute only once, right? And always procedure is execute in a loop, right? So initially, whatever you want to assign to any variable, that is right in an initial procedure. And if more than one statement, then the initial and always procedure, it is have the begin and end. Like in a C language, we have a curly bracket. So here we have the begin and the end. Okay? So begin and end. If you have only the one statement, then not need to be write the begin and end. So after the initial, directly you can write a single statement. But have a more than one statement, then it has to be enclosed between the begin and end. Similarly, the always statement, it always learn in a loop. But when it's execute, so it is execute the depend on this condition. So inside this, it is a condition means whenever having the event in A or the event in B, it will execute the statement return inside this always procedure block. So whenever having the event, at that time we want a new output. So it run sum and the carry, the logic. The difference between the continuous assignment and the procedural assignment. In a continuous assignment, like a assign, whatever we are assigned, output is equal to A and B. So this is the continuous assignment. And in procedural assignment, it is written inside the initial or the always block, right? So in a continuous assignment, variable driver nets have only types of net or wire only, right? But in a procedural assignments, driver may be the range, integer, time, different types of it support. In a continuous assignment, update the output whenever having any event in the that right hand side operand. Right? Suppose we have a assign out is equal to ending of 1 and 2. Right. So whenever having any event means change in a value. So whenever having change in even in one or in two, it will execute this statement and assign the new output to the new value to the output, right? And output must be, we have to declare as a only the wire in a continuous assignment statement. In a procedural assignment, it is written inside some procedural block. So it is run depend on this condition. If this condition is fulfilled, then it run whatever written between the begin and end statements are run. There are two types of assignment in a that always an initial block. One is the blocking assignment and another is the non-blocking assignments. So let understand what the difference between the blocking and non-blocking assignments. Blocking assignment operator is equal and non-blocking assignment operator is this less than equal. It is for the non-blocking assignment. This operator is for the blocking assignment. Right? Let's take the example. Let me define that ABCD as a range because it is we are going to use inside the initial and always. So it is always a type of range. Now here A it assigned to 0, B is assigned to 1 and has 5, and then C is equal to A and B, and then has 10, and then D is equal to A or B, right? So let's say our A signal it is equal to 0. Our B signal it is equal to 1, and let's say this is our reference time 0 time. So C will be the ending of A and B, right? But after the 5 time units, it will be change the state after the 5 time units. So initially it is an unknowns, and then after the 5 times units, this is the delay of the 5 time units. Then it is check what is the A and B. So A and B, A is equal to 0, B is equal to 1. So output still 0, right? But the D will change, have the 10 time unit delay, but it is after the 5 time unit delay because this statement are blocking assignment statement. So it run first this statement and then this statement and then it run this last statement. So it run in a sequentially one by one, right? So here after the 5 time units it is 0, then again the next 10 units, and then it check what is the input, right? So input here A is equal to 0, B is equal to 1, so D should be 1. So it is make 1, but at the 15th time units, not at the 10 time units. After the 10 time units, it is change the value after the 15 times unit because the statement if we write inside the that initial and always block and it is a blocking statement, then it is run in a sequential, right? Now we'll see same example for the non-blocking assignment. For the non-blocking assignment, let's take the same example and let me try to understand when the C and D will going to change, right? So in a non-blocking assignment statement, A is 0 and B is equal to 1. So non-blocking, this is non-blocking assignment, right? So first it run all the blocking assignment. So this A equal to 0 and B is equal to 1 are the blocking assignment. So first it run this A is equal to 0 and B is equal to 1. And then it run the non-blocking assignment statement, but all the non-blocking assignment statement run the parallel, right? So this one as well as this one run the parallel. So C is equal, C value will change after the 5 time units, right? So after the 5 times unit, C is take the value as per the A and B, but it is 0. But the D value, it take the change after the 10 time unit, not after the 15 time units. We remember if it here it is a non-blocking assignment, so it take the change after the total 10 time unit because both are run parallel, right? After the 10 time unit, it change the that it take the value A or B assigned to the D. So D will get the value after the 10 time minutes, and C will get the value after the 5 time minutes, and A and B it assign the immediately 0 and 1 at the 0 time minute. And if you see in the blocking assignment statement, so first it at the 0 time minute it assigned the A is equal to 1, A is equal to 0 and B is equal to 1. Then after the 5 time unit is assigned C is equal to A and B. And then after the 5 plus 10, after the 15 time unit is assigned the D is equal to A or B. So that's the difference between the blocking assignment and the non-blocking assignment statement. If you have any questions, you can ask by unmuting your mic. Now, non-blocking assignment statement, it is suppose if you see the procedures, how it actually works. So when we have, suppose if we want to exchange the data of A and B, right? So if we write A less than equal to B and B less than equal to A, and we know all the initial and always block are executed simultaneously. So it is unpredictable, non-deterministic that which initial block run first and which is run later on, right? So if we have the non-blocking assignment statement, then what the procedure it do? First, it take the value into a temporary variable. So first it take the value of B into a temporary variable, right? Then that temporary variable will assign to the A. Temporary variable will assign to the A. Similarly, here A value in is original this A value that is stored in a temporary variable, and that temporary variable will pass to the B. Will pass to a B. So we can exchange the data without a race around conditions, right? So the procedure is first is store in a temporary variable and then it's assigned to the operator which is on the left hand side, right? So the sequence is not important. If we write the B less than equal to A and then the A less than equal to B, or if we write the A less than equal to B and then we'll write the B less than equal to A, in both the case we'll get the same output. Sequence is not important because initially it stored the value in a temporary variable and then assigned to the left hand side operator at the end. Okay. They have different timing controls can use in a initial and always block when to run the execute, have a regular delay or intra-assignment delay, or have different types of delays possible. Let me go it very quickly. So similarly, at the rate of clock means at the positive is when the clock equal to 1, it will assign the D to Q. Right. Similarly, at the rate of opposites of clock, it will assign the D to Q. So these are the different event-based timing control. So whenever having event in this variable, it will be assigned the value to the left-hand side operator. Right. Another is the named based event. So in a Verilog, this feature is available. Right. So let's take the example. So example is, let me, here it is a provision to define any event. So here it is a user defined event. So event and the name of event, receive the data, it is one of the name of event is defined. Right. Now let's see how we can use it. Also we can trigger that events, right? So suppose if you have received the last data, so triggering is symbol is this sign and then arrow. This is the symbol for the triggering of the that event. So once this event is triggered, and we can, if we have used in any other always statement. So once this event is triggered, it run whatever we write inside that. So it can fetch the data whatever we want to perform the task. So it is an user defined event, user event event. Also we can trigger the event. Also have a OR based event. So if we have the reset event in reset or event in clock or event in D, then we want to execute the statement return inside the always. Also, or can another way we can have by putting the comma between that can be separated by comma. This also consider as an OR operator. Level sensitive operator also available. So it wait count is equal to enable, right? So when enable is equal to logic 1, after the then it have the after the 20 time unit it assign the count plus 1 to the count, increment the count at every 20 time unit if the this enable is equal to 1, right? So when enable equal to 1 it increment the count at every time unit, and when enable is equal to 0 it stop the increment the count. So this is the level sensitive timing control. In a Verilog have some conditional statement. There are three types of conditional statement available in a Verilog. If only if, so if the condition is true, then it executes some statement, otherwise nothing. And another conditional statement is if some expression is true, then it's execute the true statement, else it execute the false statement. And third is if else nested loop, right? So it's a multiple expression, and whatever the expression is true, it run corresponding statement. Let's see the syntax of if statement. If condition, then run statement as another statement. So it is easily understood if statement. If else, if control is equal to 1, then it check if control is 2 is also equal to 1, then output is equal to 4. Else means control 2 is equal to 0, then output it is equal to in 3. Else if control 1 is equal to 0, that means else if control 2 is only equal to 1, then output is equal to that second variable, second input, and else means control 1 and control 2 both are 0, then it select output is equal to first input. Case statement, case expression, and as we have taken this to implement our finite state machine hands-on session, so it's very easily understood. It's have four types of loop: while loop, for loop, repeat loop, and forever loop. While loop execute the statement or a set of statement while the condition is true. Okay? So as a condition, we can use any logical statement or any value. For a loop, as it's similar to C language, it's have initial, then increment, and this final value. Then the repeat statement. It is similar to byte, but it repeats some fixed number of times. And forever, it is run continuously until we'll end the simulation to some dollar finish or dollar stop types of directory. So while condition, then if the condition is true, it run the statement is written between the end and begin. So here is one example. So condition is if the jug is less than the jug volume. So jug volume is defined using the directive define. So jug volume is defined as 100. So and every time it add 1 cup in a jug and it check jug is full or not. Right, once it's full, it come out from the loop. For loop, it's have a initialization, condition, and update. It is similar to the syntax of C language. Repeat loop, so in a repeat loop, condition has a fixed number, so it will repeat the fixed number of times, right? So condition here is count, so count is 10, so it is repeat for fixed 10 numbers of times loop. Forever loop, it execute continuously until we end the simulation through this and finish such types of. Right. So if you want to generate a clock or any periodic signal, we can use the forever, and it is generate the clock, right? And it is end at after the 2000 time units. So it generates the clock up to the 2000 time. Task and functions. So in a very log, similar to see how the task and function. Task and function provide the ability to execute the common procedure from the several different places in the description. They also provide a means of breaking up the large procedure into the smaller ones to make it easier to read and debug the source file. And the it can pass the input, output, and an out argument value can be passed into and out of the both the task and the function. The difference between the task and functions: the function must execute in a one simulation time, but task have some time controlling statement. Function cannot enable the another task or function, but the task can enable the another task and the functions. Function must have at least one input argument, while task may not have any argument or may have more than one input argument. Function return a single value. That's the main difference between the task and function. The function return a single value, but task does not return any value, right? The purpose of function is to respond the input value and returning a single value. So it will pass some single input value and do some mathematical or whatever the operation you want to do, and then it function will pass the result into the main program. Task can support the multiple goals, can calculate the multiple result. However, only the output and in-out argument can pass through the invocation through the task. Verilog model use the function as an operand, but as an expression. The value of operand, the value of return by the function, right? So whatever the value of return by the function can be assigned to a another operand on the left hand side. Syntax of the task. We already use task when we have seen the EDA playground one example for the display task. So it is a task and whatever the task name and task may contain whatever it is in a module, same thing it can have inside the task, right? So task name and then whatever you want to perform, it not returned any value to the main program, but it performs some task which we want to needed to perform multiple times in program. We can write the task of it. Function variable type and function name, right? So function return the value. So function integer add. So add value will be returned back to the main program. So let's take calling of task and function. So task can call by writing just the name of task with a passing parameter, whatever the parameter you want to pass. So task, and if we don't want to pass any parameter, just write the task name. If you want to pass parameter, write the task name in bracket the parameter. And the function we can use as an operand. The return value of function we can use as an operand. So here we can see the function name with the passing of this function parameter, and whatever the return by this, it will be assigned to the data types. So function can also use as an operand to assign another operand on the left hand side, but task cannot. These are the program written in a different architecture modeling, which we already gone through it. I have used reference book Samir Palnitkar on a Verilog HDL to prepare this my presentations. Thank you. If you have any questions, you can ask. Thank you. If you have any questions, you can ask. Okay, thank you. Sorry. Now our next session is tomorrow, 11 o'clock on a DFT designed for testability, right? So our next session, third day, first session is on 11 o'clock tomorrow. You can now leave the meeting. If you do not have any question, you can leave the meeting.
I
I will upload the PPT and the design which we have taken to implementation of Verilog code, everything on a MST. So you can access the material. Let me, this is already in a shared screen. So you can access the material, go to in a team, and here you can find the material in the file sections, right? Here you can, I also upload today my presentations and that we have, whatever we have designed in Verilog, everything I will upload here. You will find from any material in a file section. Also, I will upload the presentation received from the yesterday's expert. Any questions? Then let me end our meeting.